Steel, a symbol of strength and resilience, has been the backbone of civilizations for over 4,000 years. Originating in ancient Anatolia and Sri Lanka, steel's journey from raw iron to the backbone of skyscrapers is a testament to human ingenuity. Today, it's integral in everything from infrastructure to the utensils we use daily, contributing to a global industry worth billions. So, how is it made? The journey of steel begins with its primary raw material, iron ore. Extracted from the earth through mining operations, iron ore is found in abundance in countries like Australia, Brazil, and China. These large, reddish-brown rocks are rich in iron oxides and vary in color from dark gray to deep purple and rusty red. Alongside iron ore, coking coal, a high-carbon fuel essential for steel making, is sourced primarily from regions like the Appalachian Mountains in the USA and parts of Australia. Limestone, another vital component, is widely available globally. Iron ore undergoes a process called beneficiation to increase iron content and remove impurities. This involves grinding the ore into a fine powder, followed by magnetic separation and flotation techniques. The powdered ore is then mixed with water and reagents, creating a slurry. Magnetic separators attract magnetic iron particles, effectively separating them from non-magnetic waste. Meanwhile, coking coal undergoes a process called coking to remove impurities and increase carbon content. This is achieved by heating coal in the absence of air in coke ovens, transforming it into coke, a porous, hard and gray substance. The initial processing of steelmaking starts in a blast furnace, a towering structure often standing over 30 meters tall. Iron ore, coke, and limestone are the key ingredients fed into the furnace. Here, the intense heat of over 2,000 degrees Celsius, or 3,600 degrees Fahrenheit, triggers a series of chemical reactions. The coke acts as both a fuel and reducing agent, breaking down iron ore into molten iron. The limestone serves as a flux, combining with impurities to form slag, which is lighter and floats on top of the molten iron. In this inferno, the iron ore undergoes a reduction process. Oxygen atoms are stripped away from the iron oxide in the ore, leaving behind liquid iron. This molten iron, also known as pig iron, has a high carbon content, making it brittle and unsuitable for most applications. To refine it further, the pig iron is then transferred to a basic oxygen furnace, BOF, or an electric arc furnace, EAF, depending on the production method. The BOF method introduces pure oxygen into the furnace to further reduce carbon content. The oxygen reacts violently with the carbon, creating carbon monoxide and carbon dioxide gases that escape the molten metal. Alternatively, the EAF method, primarily used for recycling scrap steel, melts the scrap using high-powered electric arcs. This process also reduces the carbon content and impurities, but relies heavily on electrical energy. Both methods allow for precise control over the final composition of the steel, ensuring the desired balance of carbon and other elements like manganese, silicon, and phosphorus. Once the raw iron has been converted to steel with lower carbon content, it's time for the main manufacturing process, which refines the steel into a usable form. This stage is crucial, as it determines the physical and chemical properties of the final product. In the basic oxygen furnace, BOF, after the carbon content is reduced, alloys and other materials are added to achieve the desired steel grade. Common additives include manganese for increased strength and toughness, nickel for corrosion resistance, and chromium for hardness and durability. The precise composition is carefully controlled, as even minor variations can significantly alter the steel's characteristics. The steel is then subjected to a process known as ladle refining, where further adjustments are made, including deoxidation and desulfurization. This process removes residual elements that could weaken the steel, such as sulfur and oxygen. Temperature control is vital during this stage. The steel must be kept at a consistent temperature, usually around 1,650 degrees Celsius, or 3,000 degrees Fahrenheit, to maintain its molten state and ensure proper mixing of the additives. This is achieved using ladle furnaces, or through the injection of gases like argon to stir the molten steel, promoting homogeneity. The next phase involves casting the molten steel. The two primary methods are continuous casting and ingot casting. Continuous casting is the most widely used method due to its efficiency and cost-effectiveness. The molten steel is poured into a water-cooled mold, where it solidifies into a slab, bloom, or billet. These semi-finished forms are then sent for further processing. In contrast, ingot casting involves pouring the steel into large molds where it solidifies. These ingots are then reheated and rolled into desired shapes. However, this method is less efficient and more time-consuming compared to continuous casting. After casting, the steel undergoes primary forming processes, including hot rolling, where the steel is passed through large rollers while still hot. This process shapes the steel into various forms like sheets, plates, bars, and rods. The hot rolling process not only shapes the steel, but also improves its mechanical properties, like toughness and ductility. The steel's surface is also treated during this phase to remove scale, a layer of iron oxide that forms during heating. Scale removal is done using high-pressure water jets or by passing the steel through scale breakers. Cold rolling follows hot rolling for some steel products. This involves further rolling the steel at room temperature to achieve tighter tolerances and better surface finishes. Cold rolling hardens the steel, making it stronger and more resistant to wear and tear. However, it also makes the steel more brittle, which is why some steel types undergo annealing, a heat treatment process where the steel is heated and then slowly cooled to reduce hardness and improve ductility. Coating is another critical part of the steel manufacturing process. Depending on the intended use of the steel, different coatings are applied for added protection. For instance, galvanizing, which involves coating the steel with a layer of zinc, protects against corrosion. Similarly, tin plating is used for steel intended for food packaging, while color coatings are applied for aesthetic purposes in construction materials. Quality control is a continuous process throughout steel manufacturing. Various tests and inspections are performed to ensure the steel meets the required standards and specifications. These include tensile tests to measure strength, hardness tests, and microstructural analysis using electron microscopes. Non-destructive testing methods like ultrasonic and radiographic testing are also employed to detect internal flaws without damaging the product. Towards the end of the main manufacturing process, the steel undergoes finishing operations. These include cutting to specific lengths, surface grinding to achieve the desired texture, and shaping or bending for specific applications. The finished steel products are then subjected to final inspections and quality checks before being approved for shipping. Throughout the manufacturing process, environmental considerations are also taken into account. Steel plants employ various measures to reduce their environmental impact, such as using dust collection systems to minimize air pollution, treating wastewater before discharge, and implementing energy-efficient technologies to reduce greenhouse gas emissions. The adaptability and versatility of steel make it an essential material in numerous industries, from construction and automotive to appliances and packaging. The combination of strength, durability, and recyclability makes steel a material of choice for sustainable development, playing a crucial role in building a greener future. Once the steel has passed all quality checks, it enters the final stage of packaging. This involves bundling and securing steel products like rods, bars, and sheets using heavy-duty straps for safe transportation. For some products, additional protective layers, such as waterproof paper or plastic wraps, are used to prevent corrosion and damage during transit. The packaged steel is then labeled with relevant information, including grade, size, and tracking details, ensuring traceability. Finally, it's loaded onto trucks, ships, or trains, ready for distribution to various industries, signifying the end of its journey from raw ore to a foundational building block of modern society. In conclusion, steel manufacturing is a complex process, blending ancient methods with modern technology. From the reduction of iron ore in blast furnaces to the precision of continuous casting and rigorous quality control, the journey of steel exemplifies human engineering prowess, culminating in a versatile material central to our daily lives.
An astounding 10 tons of raw platinum ore is required to produce a single ounce of pure platinum, and its value is approximately 30 times that of gold, showcasing the extraordinary rarity and worth of this prestigious metal. Discovered in the 18th century by Spanish explorers in the New World, platinum was initially seen as a nuisance by the conquistadors, who were unaware of its potential and threw it away in their search for gold. Today, platinum's remarkable properties are harnessed in catalytic converters to reduce vehicle emissions, in medical implants and equipment due to its biocompatibility, and in electronic components for its excellent conductivity and durability under extreme conditions. This metal's application in industrial catalysts also plays a crucial role in the production of silicone and other chemicals. So how is it made? The production of platinum begins deep in the Earth's crust, where platinum ore is mined in a few select areas around the globe, primarily in South Africa, which accounts for over 70% of the world's platinum supply, followed by Russia and Zimbabwe. The extraction process starts with the mining of platinum-containing materials, such as sperrylite and cooperate, which are platinum-bearing minerals. These precious ores are located up to 3 kilometers, nearly 2 miles, below the surface, requiring extensive and deep underground mining operations to access the valuable platinum group metals they contain. The mined ore undergoes a series of crushing and grinding processes to break down the rock and release the platinum-bearing minerals. Heavy-duty jaw crushers, which apply mechanical pressure to the ore to break it into smaller pieces, initiate this process. Following this, cone crushers further reduce the size of the crushed ore, utilizing a gyrating spindle to compress the material against the outer walls of the crusher, achieving finer particles suitable for the subsequent stages. This is followed by flotation, a process that involves mixing the crushed ore with water in special regions to make the platinum particles hydrophobic, allowing them to attach to air bubbles and rise to the surface in a froth that can be skimmed off. Following flotation, the concentrated platinum ore is subjected to a smelting process. Here, it is heated to over 1,500 degrees Celsius or 2,700 degrees Fahrenheit in a furnace, causing the metals to melt and combine with a flux. This forms a matte layer that contains the platinum group metals, including platinum, palladium, rhodium, ruthenium, iridium, and osmium, which is heavier and sinks to the bottom, allowing it to be separated from the slag. The matte is then transferred to a converter, where air is blown through it. This oxidizes the iron and sulfur, which are removed as slag. What remains is a concentrated bulk of platinum group metals. This concentrated mass undergoes further refining processes, including leaching with aqua regia, which is a mixture of hydrochloric and nitric acid that dissolves the metals. The solution is then subjected to a series of chemical reactions that separate and purify the individual metals. After the refining process, the purified platinum is ready for its final transformation into the valuable products we use. This stage begins with the platinum, now in its pure form, being melted in a furnace at temperatures exceeding 1,800 degrees Celsius or 3,200 degrees Fahrenheit. This molten platinum is then cast into molds to form ingots or directly used in various manufacturing processes depending on its intended application. In the case of industrial applications, platinum is often alloyed with other metals to enhance its properties for specific uses. For example, in catalytic converters, platinum is combined with palladium and rhodium to maximize its effectiveness in converting harmful emissions from vehicle exhausts into less toxic substances. For medical applications, the biocompatibility of platinum makes it ideal for use in pacemakers and implantable defibrillators. Here, platinum's ability to conduct electrical signals without corroding in the body's environment ensures the long-term reliability of these life-saving devices. In electronics, platinum's exceptional conductivity and resistance to corrosion find it a role in manufacturing high-end computer components and mobile devices. This involves depositing thin layers of platinum onto silicon wafers or other substrates, a process requiring advanced techniques such as physical vapor deposition. Platinum is crucial in enhancing the performance of computer hard drives and in the production of high-precision resistors and capacitors, ensuring devices operate more efficiently and reliably under extreme conditions, such as high temperatures and corrosive environments. Furthermore, the production of jewelry and fine watches utilizes platinum for its aesthetic appeal and durability. Skilled artisans and jewelers craft platinum into various designs, emphasizing its luster and strength. The creation of platinum jewelry involves several stages, including casting, forging, and hand finishing to achieve the desired quality and finish. Given its rarity and high value, recycling platinum has become not just a necessity, but a lucrative business. The process of reclaiming this precious metal from various sources, be it spent automotive catalysts, electronic equipment, or industrial catalysts, plays a critical role in sustaining its supply. Remarkably, it's estimated that up to 30% of the platinum used in manufacturing and consumer products is recovered through recycling. This significant recycling rate is essential as it substantially reduces the demand for newly mined platinum, ensuring a more sustainable approach to meeting global needs. The recycling process begins with the collection of platinum-containing materials. Automotive catalytic converters, a primary source of recyclable platinum, are gathered from scrapped vehicles. In electronics, platinum is recovered from circuit boards and other components where it's used for its conductive properties. The collected items are then processed to extract platinum and other valuable metals such as palladium and rhodium. The ability to recycle platinum and other precious metals efficiently is crucial for the future of technology, automotive industries, and environmental conservation. As techniques and technologies for recycling continue to advance, the percentage of platinum reclaimed and returned to the market is expected to grow, further emphasizing the importance of recycling in the platinum supply chain. One of the main challenges in platinum recycling is the separation process. Due to the complex nature of the materials being recycled, which often contain a mix of different metals and non-metallic substances, advanced separation techniques are required. Pyrometallurgical processes involving high-temperature treatment are commonly used to burn off the non-metallic components and separate the metals. This is followed by hydrometallurgical processes, which use chemical leaching to further refine and separate the platinum from other metals. The equipment used in these processes must be capable of withstanding high temperatures and corrosive chemicals. Furnaces for the pyrometallurgical process and leaching tanks for the hydrometallurgical process are key pieces of equipment. Which metal do you want to hear about next? Let us know in the comments. Every minute, over 50 tons of aluminum are produced worldwide, enough to build over 60 airplanes, showcasing the metal's critical role in various industries. In the United States alone, the annual production value of aluminum surpasses $40 billion, and the global market value is expected to reach $350 billion by the end of the decade. This all began with a revolutionary discovery in 1886 by Charles Martin Hall and Paul Héroult, who found a method to extract aluminum from its oxide alumina. This innovation drastically reduced the metal's cost, making it widely accessible for the first time. So how is it made? It all starts with bauxite, the primary source of aluminum. This reddish clay material, rich in aluminum oxides, is predominantly found in tropical and subtropical areas, including countries like Australia, Brazil, and Guinea. The extraction of aluminum begins with mining bauxite, which is then subjected to preliminary treatments aimed at removing impurities and increasing the aluminum content. These initial steps typically involve washing and crushing the ore. The refined bauxite undergoes the Bayer process, developed in the late 19th century, which produces alumina from bauxite. Here, bauxite is mixed with a hot sodium hydroxide solution, which separates the aluminum-containing components. The mixture is then cooled, causing alumina to precipitate out, resulting in a white powder that serves as the key ingredient for aluminum production. After the extraction of alumina, it is purified to remove any lingering impurities, ensuring the aluminum produced meets high-quality standards. The refined alumina is then transformed into metallic aluminum through the Hall-Héroult process, marking its transition into the versatile material used in a wide range of products and applications globally. Technological advancements from the initial discovery to today's highly efficient production techniques have exponentially increased our capacity to produce aluminum. These developments have enabled the production of millions of tons of aluminum annually, meeting the growing demand across various industries. Once alumina is derived from the Bayer process, it enters the next phase to become metallic aluminum. This critical stage transforms the white alumina powder into the versatile metal. In this process, alumina is dissolved in a molten bath of cryolite, which brings the melting point of alumina down from 2050 to 950 degrees Celsius, or 3,700 to 1,750 degrees Fahrenheit. This lower melting point allows for the efficient conduct of electrolysis. The process involves passing a strong electric current through carbon electrodes immersed in the molten bath. This current breaks the alumina down into aluminum and oxygen, with the oxygen reacting with the carbon electrodes to create carbon dioxide and leaving behind molten aluminum metal at the bottom of the cell. Molten aluminum is collected from the bottom of the electrolytic cell at regular intervals. The operation is sustained by continuously adding alumina to the electrolyte and extracting aluminum, maintaining a steady production flow. The energy demand for aluminum production is substantial, necessitating large amounts of electricity to sustain the electrolysis. Consequently, aluminum manufacturing facilities are often situated near abundant power sources, notably hydroelectric power plants, to reduce energy costs. This high energy requirement has spurred efforts within the industry to enhance process sustainability through energy recuperation and recycling initiatives. After the molten aluminum is extracted, it is either cast into ingots for standard use or molded into specific shapes for specialized applications. These ingots are the basis for further manufacturing processes, including rolling and extrusion, which tailor the aluminum for diverse uses. After the initial extraction and casting into ingots or specific shapes, the next step involves transforming these basic forms into a variety of products like plates, rolls, rods, and notably, aluminum foil. This transformation is achieved through different processing techniques tailored to the desired end product. For aluminum plates and sheets, the process begins with heating the ingots to a malleable state. These heated ingots are then passed through rolling mills, which systematically reduce their thickness. The precision in this rolling process determines the thickness and quality of the aluminum plates and sheets, making them suitable for applications ranging from construction to automotive manufacturing, where durability and lightweight are essential. In the production of aluminum rolls and rods, the process similarly starts with heating. However, the focus shifts to creating longer, thinner forms. Rods are formed by extruding the heated aluminum through dies with precise diameters, resulting in products used in electrical applications due to aluminum's excellent conductivity. Rolls, on the other hand, are created by coiling the aluminum sheets or plates post-rolling, useful in packaging, including the food industry, for their protective qualities against moisture and other environmental factors. Aluminum foil stands out for its unique manufacturing process and utility. The production of foil involves an additional rolling step where sheets are passed through a series of mills to achieve the remarkably thin gauges required for kitchen use and industrial applications, often less than 0.2 millimeters. The extreme thinness of the foil makes it ideal for wrapping foods, reflecting heat, and serving as a barrier against light, odors, and moisture, preserving freshness and preventing contamination. Post-processing treatments such as anodizing or coating aluminum products enhance their natural properties. Anodizing, for example, increases corrosion resistance, surface hardness, and wear resistance, making the aluminum more durable and aesthetically pleasing. This treatment is particularly beneficial for architectural components and outdoor furniture, where longevity and visual appeal are key considerations. Throughout the manufacturing process, rigorous quality control measures are in place to ensure that the aluminum products meet strict standards for their intended uses. This includes testing for mechanical properties, corrosion resistance, and dimensional accuracy, ensuring the aluminum's performance in its final application. Once aluminum has been processed into its final form, be it plates, rolls, rods, or foil, it undergoes final packaging to ensure the product reaches consumers and industries in perfect condition. This stage is tailored to protect the aluminum products during storage and transportation, safeguarding them against environmental factors and physical damage. Aluminum plates and sheets are typically stacked and wrapped in heavy-duty plastic or waterproof paper to prevent moisture damage. They might also be strapped to pallets, making them easier to handle and transport. This method keeps the plates and sheets secure and prevents surface damage that could impair their utility in applications requiring high precision and aesthetic quality. Rods and rolls, due to their different shapes and uses, have unique packaging requirements. rods are often bundled together and wrapped in plastic or banded to secure pallets for transport. This packaging ensures the rods remain straight and undamaged during handling. Aluminum rolls, particularly those used for foil or thin sheets, are protected by robust cardboard cores inside the rolls and wrapped in plastic or paper to prevent unrolling and surface contamination. Aluminum foil, known for its delicate nature and extensive use in food packaging and preservation, receives special attention. Rolls of foil are packaged in cardboard boxes that serve not only as protection, but also as dispensers. These boxes often feature a cutting edge, making it convenient for consumers to cut the foil to size. The packaging design for aluminum foil focuses on ease of use, protection, and preserving the foil's cleanliness and hygienic properties until it is ready to be used. Titanium is as strong as steel, but 45% lighter, providing significant benefits in efficiency and performance for industries such as aerospace, military, and sporting goods. Its identification by William Gregor in the 18th century marked a milestone, and over time, its extensive utility and superior properties have not only transformed engineering paradigms, but also significantly contributed to medical advancements through its biocompatibility. In 2023, the global market value of titanium was projected to grow to nearly $31 billion, reflecting its indispensable role across various sectors and highlighting its critical importance and the innovation it brings to modern manufacturing and technology. So how is it made? The production of titanium begins with the extraction of its primary ore, ilmenite and rutile, from the earth. These ores are predominantly found in mineral sand deposits spread across various parts of the world, with significant concentrations in Australia, South Africa, Canada, and Norway. The extraction process involves dredging or dry mining techniques where the ore is separated from the sand using gravity and magnetic separation methods. Heavy machinery and specialized equipment are employed for the extraction. In dredging, large ships with dredging equipment scoop up mineral-rich sand and transport it to a processing plant. For dry mining, bulldozers and excavators uncover and transport the ore to the processing facility. At the facility, further separation using high-tension rolls, electrostatic plates, and magnetic separators efficiently isolates the titanium ore. Once extracted, the raw titanium ore undergoes a series of treatments to extract the titanium dioxide, used as a white pigment in paints, sunscreens, and food colorings. This involves chlorination in the presence of petroleum coke, converting titanium ore into titanium tetrachloride through the Kroll process. This process not only serves industries requiring the pigment, but also marks the beginning of transforming titanium ore into a metallic form. The titanium dioxide it is further refined through calcination, where it is heated at high temperatures to result in a pure, powdery form. This refined titanium dioxide is then packaged and distributed for use in various industries, enhancing the color and opacity of products with its brightness and high refractive index. Shifting focus back to titanium metal production, the Kroll process remains the dominant method. This involves reducing titanium tetrachloride with magnesium in a sealed reactor at temperatures exceeding 900 degrees Celsius, or 1650 degrees Fahrenheit, producing titanium sponge and magnesium chloride. The titanium sponge then undergoes vacuum distillation to remove excess magnesium and magnesium chloride, resulting in pure titanium. The sponge is melted in either a vacuum arc furnace or through electron beam melting to produce ingots. The vacuum arc furnace creates an electric arc between the titanium sponge and electrodes within a vacuum, melting the sponge without introducing impurities. Electron beam melting uses a high-energy beam of electrons focused on the titanium, melting it in a highly controlled manner. These ingots can then be processed into various shapes and sizes through forging, rolling, and extrusion to meet specific industry requirements. This series of processes from ore to finished product not only requires significant energy input, but also precise control to ensure the titanium meets the high-quality standards required for its end use in aerospace, medical implants, and other critical applications. The next steps focus on refining these ingots into the final, application-specific products. The process from ingot to a finished piece involves intricate and specialized techniques tailored to the unique requirements of each industry utilizing titanium. Initially, the ingots are subjected to heat treatment. This critical process adjusts the titanium's microstructure, optimizing its strength and flexibility. The precision in the heat treatment process is vital for applications where titanium's strength-to-weight ratio is essential. Subsequently, the titanium undergoes machining, where it is shaped into its final form. Due to titanium's inherent toughness, this stage necessitates the use of specialized machining tools and techniques. Milling, turning, and drilling transform the titanium into a myriad of parts, from intricate medical implants to robust components of aircraft. Efficiency in the machining process is paramount, given the high value of titanium and the intensive energy required in its production. To achieve the necessary surface qualities and ensure functionality, titanium parts often undergo additional finishing processes after machining. These processes, including grinding, polishing, and sometimes coating, are tailored to the specific needs of the product. Whether it's achieving a smooth finish for biocompatibility in medical implants or applying protective coatings for enhanced durability in aerospace applications. Quality control is a continuous theme throughout the titanium manufacturing process, ensuring that each product not only meets but exceeds the demanding standards of its application. Dimensional accuracy, material composition, and functional performance are rigorously tested, often using advanced non-destructive methods such as ultrasonic testing to identify any internal discrepancies without damaging the part. Once titanium has been transformed into its final form, it is utilized in various sectors, each with unique applications that leverage titanium's exceptional properties. In automotive engineering, titanium enhances vehicle performance and efficiency, especially in high-end and performance vehicles that use it in valve springs and exhaust systems. Titanium valve springs reduce engine weight, improve efficiency, and allow higher rev limits. Titanium exhaust systems, lighter and resistant to corrosion and high temperatures, result in durable and high-performing setups. These components are precision-engineered from titanium alloys to meet the demands of automotive performance, blending strength, durability, and lightness. In the aerospace industry, titanium is vital due to its strength-to-weight ratio and corrosion resistance. It's used in structural components like fuselages and engine parts, crucial for their durability under extreme conditions. Titanium compressor blades in jet engines highlight its tolerance to high temperatures and stress, leading to more efficient and powerful engines. Additionally, titanium finds use in fasteners, landing gear, and hydraulic systems, exploiting its properties to improve aircraft performance and safety. In the medical sector, titanium stands out for its biocompatibility, making it ideal for implants such as hip and knee replacements. These devices are engineered to replicate the movement of human joints, enhancing mobility and reducing pain for patients. The key attributes of titanium, including its resistance to corrosion by bodily fluids and its capacity to bond with bone tissue, ensure the durability and success of these implants. Precision machining and 3D printing are utilized in their production to achieve components that precisely fit individual patient anatomy. Beyond joint replacements, titanium's applications extend to dental implants, bone screws, and pacemakers, capitalizing on its non-toxic and strong properties. This direct application of titanium in healthcare highlights its crucial role in advancing medical treatments and improving patient outcomes. Titanium recycling is essential for industry sustainability, with around 30% of titanium in manufacturing coming from recycled materials. This process reduces the environmental impact and saves the energy needed for titanium production from ore. Recycled titanium primarily comes from industrial scrap, defective parts, and end-of-life products. A key step in recycling is separating titanium from other metals and impurities, using magnetic separation and other sorting methods. The cleaned scrap is then melted in a vacuum or inert atmosphere to prevent contamination. This recycled titanium can be used directly for casting or transformed back into sponge form and processed through the Kroll process, similar to virgin titanium ore. Recycling titanium consumes only about 5% of the energy needed for production from ore, significantly lowering its environmental footprint. Did you know that almost all the gold discovered today did not originate on Earth? Instead, it came from meteorites that hit our planet 200 million years after it was formed. Gold, an element that has fascinated humans for millennia, is not just a symbol of wealth and power. but also a cornerstone of the global economy. With an industry generating almost $200 billion in revenue annually, gold remains a highly sought-after metal. The journey from the ground to gleaming bars involves a complex and technologically advanced process. From identifying potential gold-bearing areas to the final refinement stages, the transformation of raw gold into bars demonstrates human ingenuity and the relentless pursuit of value. So how is it made? The quest for gold begins with the meticulous identification of potential gold-bearing areas. Geologists and mining companies conduct extensive surveys, prospecting, and geological studies to pinpoint regions with promising gold deposits. This search may involve analyzing geological maps, conducting soil sampling, and employing advanced techniques like remote sensing or geophysical surveys to locate these elusive deposits. Most gold comes from lode deposits, also known as vein deposits, where gold is concentrated along with other metals in the cracks of rocks. Once a potential gold deposit is identified, the site is prepared for mining. This preparation includes clearing vegetation, constructing access roads, and establishing necessary infrastructure like camps and facilities. These initial steps are crucial for setting the stage for the mining operations that follow. The extraction of gold-bearing rock, called ore, involves hard rock mining, which is a labor-intensive process requiring drilling and blasting to remove the ore from the earth. Specialized machinery and equipment are brought in, including long-hole drill rigs and mucking machines, to assist in this initial phase of gold production. The raw materials, essentially the gold-bearing ore, are then ready to undergo a series of processes to eventually be transformed into the pure gold bars that symbolize wealth across cultures and economies. After extracting gold-bearing ore from the earth, the initial processing begins with crushing and grinding the ore into smaller particles. This preparation is crucial for the subsequent chemical reactions and extraction processes. A mill pulverizes the ore to the texture of beach sand, increasing the surface area for the chemicals to act upon. The factory then introduces a water and cyanide solution to the pulverized ore, further grinding it into a mud-like slurry. This slurry flows into large settling tanks, where the heavier wet solids sink to the bottom, separating from the water. This stage involves a critical process called aeration or air agitation. Workers transfer the wet solids into an agitation tank and introduce air, initiating a chemical reaction between the cyanide and the gold trapped in the ore. This process, known as leaching, triggers the gold to dissolve into the surrounding water, forming a gold-cyanide complex. The efficiency of this process is paramount, as it determines the amount of gold that can be extracted from the ore. The slurry, now enriched with gold, is sent to drum filters for filtration, separating the gold-laden water from the solid impurities. This phase is vital for concentrating the gold and preparing it for the next steps in the purification and refining processes. The initial processing sets the foundation for transforming raw gold into a form that can be further refined into the pure gold bars that hold immense economic and symbolic value. The enriched gold-laden slurry undergoes a series of meticulous refining processes to extract pure gold. The precipitated gold, extracted through the drum filters, still contains impurities and is not yet ready for the market. It enters the smelting phase, where it is subjected to high temperatures in a furnace. This process separates the pure gold from other metals and impurities present in the alloy. The intense heat causes the denser gold to settle at the bottom, forming door bars, a semi-pure alloy of gold that marks the transition towards purity. These door bars, containing gold and other metals, are then sent for further purification. Electrolysis or chemical leaching processes dissolve the door bars, meticulously separating pure gold from the remaining impurities. This stage is critical, ensuring that the final product meets the stringent 99.9% purity standards demanded by the global market. The pure gold is then cast into bars, each stamped with its weight and purity. Each bar is carefully handled with gloves to prevent any smudges or corrosion from direct contact with human skin. They are then wrapped in high-quality protective materials that safeguard against scratches and environmental elements. The packaged gold bars are sealed and labeled with all pertinent information, including weight, purity, and a unique serial number for tracking and authentication purposes. This information serves as a certificate of authenticity and quality assurance for buyers and investors. The bars are then placed into secure containers, ready for shipping. The final packaging and secure distribution of gold bars encapsulate the culmination of a complex process of transformation from raw ore to a refined investment commodity. Each bar's journey from the depths of the earth to the vaults and safes of its final holders is a remarkable testament to human endeavor in the pursuit of value and beauty.